To those of you who missed my morning keynote, a little bit about me. I was a PhD student at the Hebrew University, and then I was a postdoc at Carnegie Mellon, and starting working on the GraphLab open source project that started around 8 years ago. Once the project became more popular, we opened a company in Seattle, which is called Datto. I'm heavily involved in recommender system research. That was my research topic in my postdoc, and also in some recommender conferences. So this year we have a conference in Boston, a workshop called LSRS. It's large-scale recommender systems. And this is the first year it's already been going jointly with Pandora. We are organizing it. And this short talk is going to be about what's the status of recommender systems in industry. So I'll talk less about Datto and more about what we see around and what are the trends. Although I will give a lot of examples. So we are a Seattle-based company. We have 50 people in Seattle, and we have a small office in Israel where I'm based. So when we start to talk about recommender system, one of the most influential events that shaped recommender research was the Netflix competition. I guess all of you probably have heard about it. It was kind of famous. And at the end of the competition, a winning team received a prize of $1 million. So that was a very big prize. And by the way, to the left, there is Dr. Yehuda Koren. He's Israeli, so it's nice to know that Israeli won this competition. And I'm going to talk a little bit about why this is important and what are the current trends we see, and some insights based on this competition. So to give you a little more details about what was the data in this competition, so basically it was kind of a very simple data set where we had persons, some ideas of persons, and we have the movies they have observed. And for each movie we had a score in stars between 1 to 5 to signify whether Alex liked Game of Thrones, 5 stars, and so on. So relatively to its time, it was a relatively big data set back then. It had 100 million ratings. Today we consider it as kind of a small data set, but back then it was considered very big. And we had 500,000 users, so also it was considered kind of a demanding data set, especially with the computation, the availability of computing hardware that were 10 years ago is not what we have today, of course. So let me tell you a little bit about the competition outcome. So as I said, the winning team won $1 million. If we get in a little more detail, the winning algorithm was actually a combination of different methods. And the way it worked, a few teams started to compete in this competition, and then they started to make a coalition together, so the teams got merged, and whenever a team got merged, they merged their own few solutions together in order to improve the accuracy. So at the end, it was kind of a mess of a lot of different algorithms, a lot of different methods combined together, 107 different methods. And also the computation, even the data set was relatively small, so it wasn't even it's something like 2% back then of the total Netflix data. Still, it took around 2,000 hours to compute all, you have a lot of methods, so you need to compute them all in parallel, and it takes a lot of computing hours. To those of you who know a little bit about recommender research, so typically the methods used was matrix-based factorization. That was kind of the basic methods with some variants, and also some item-based methods. So that was kind of the state of the art back then. So what's interesting about the insights learned from this competition? So the first thing which I find very interesting, and I find it always appearing in any data science project everywhere, that's my 80-20 rule. So basically, after 1 year of the competition, Netflix paid $50,000 as a progress prize. And the progress prize after 1 year was able to gain improvement of around 8.5% in the rating accuracy of Netflix. So that was very good for Netflix, and actually the solution was relatively simple, and they were able to incorporate it in production. On the other side, after 2 more years of the competition, Netflix paid $1 million as the full solution, but the full solution only improved 9.5% of the original accuracy, which means it improved just 1% over the baseline progress price. So that was kind of annoying. And also, when you look into it, Netflix never actually implemented this in production. And here I have a quote by Javier, who is one of the, back then he was one of the senior engineers at Netflix, now he's in Quora, that actually it wasn't worth it to implement this kind of solution in production. So of course now we are much smarter, but it should have been good to tell the Netflix guy, hey, wait, stop after 1 year. No point in over-optimizing the kind of fourth digits of the solution. Another interesting anecdote about this competition is that actually there was a Hungarian team who had the exact same accuracy up to the 4 digits after the decimal point for the solution. So actually both teams submitted the same solution, and it was 20 minutes apart the submission. So the Israelis got lucky and their solution was first, or else the Hungarian would win. So the Hungarians were very good, but of course they didn't receive anything out of this. So why am I talking now at the Netflix, which is kind of old and well-known? And the situation in industry is that whenever a company approaches and needs to implement recommenders, then they basically say, okay, let's look what's the state-of-the-art knowledge. Oh, there was the Netflix competition. There are many tools that solve them. So now let's begin with that, and let's continue from there. And this is kind of the common mistakes that we see, that companies are sure that everything is solved, but when they come to look at their own problem in more detail, then they start to realize that basically more work is needed. And it's not exactly like Netflix. And why is that? There are a few issues which raise up from the setting of this competition. So the first one is related to the cost function, and a lot of academic paper and a lot of discussion, even through the competition, mentioned the fact that they kind of selected the wrong cost function to the one we like to choose. And in a minute I will say why. And also there was some issue by the way the data is modeled and handled, and also about the usability, because basically the solution was not usable whatsoever, so they just basically didn't use it. So what about the cost function? So the cost function in Netflix tried to minimize the average error. And the average error is not that interesting when we present items to user. The reason is that, let's say I like a movie 3.5 or 3.6. It anyway doesn't matter to a human. What's more interesting is that if I have 3 movies, if I have a recommendation for 3 movies, I want to get the first movie that I will like the most to be first, without relation to the average error. So it's more of a ranking problem. I want to get my top choice, and it doesn't matter if my top choice is 2.5 or 3.7 or whatever, but I want to get the one that I will actually see. So that's one issue. And after that, there have been a lot of recommendations about different types of ranking cost function, and there are many of those, and there are a lot of academic papers about that. Many times when we talk to customers, they actually tell us things in a business language, and they say, okay, we don't want to average the to minimize the average cost. They don't know what's the average cost and so on. So they say, I want to increase user engagement on my website, or things like that. And then it's really not clear what they actually want. Do they want the user to spend more time on the website? Do they want the user to watch more movies? Do they want the user to be more happy or whatever? So maybe I watched a lot of movies, but they were all sucked and I was upset. So it is very difficult to actually understand what's the business goal and then try to map it towards the actual machine learning type optimization. So one of the assumptions in Netflix was that we actually know who are the users, but in many cases in practice we find out that a lot of companies don't know who are the users who surf to their website. And the reason is that many news sites and supermarkets and other types of sites, the users don't register at all. They just come up. Sometimes they buy even without signing up, or so we are not sure, or maybe they are new users and we don't know anything about them. So there are a few interesting companies. One of them is Israeli, and they are here, Crosswise. which try to solve this problem in the sense to try to identify multiple, the same user which surfs from multiple devices. So if I come to home and I watch the web from my TV and then I go to my iPhone, we would like to link that this is the same person. No point in showing them all over the same ads, because then we waste our marketing budget. And this is, as I said, related also to what we call the cold start problem, that if a new user comes in, even if the user is signed up, I don't know what the user likes. So it is a problem to actually recommend to him. So the Netflix competition didn't include any thought about what happens if there is a new user. What should I do? We have no clue, basically, what to do. So I want to start with the first demo. I'll show you a few demos here to make the talk more interesting. And the first demo, let me see, I hope the internet will work, of course. Yeah, so this is what we call a pathways demo, and it's an item-based model. What we have here, we have Amazon dataset, where I can click on any, put in any item sold in Amazon. So I like Jim Carrey movie, this is a stupid movie, so I'm getting all the other stupid movies that are typically consumed together. So I can tell you based on this model that if I like Jim Carrey movie, most likely I will be recommended by this model other Jim Carrey movies, or Rocky IV and Rocky V, which are all stupid movies. So I know the model is working well. Now what happens in practice is typically whenever I'm trying to see a movie with my wife, she always likes drama, and she tells me, why do you watch all these stupid movies? I like to see something meaningful. I like to see Sense and Sensibility, which is a Jane Austen novel turned into a movie. And what we can do for you, for your marriage, is actually try to compute the path that links our preferences. And let me explain how it works. So my wife wouldn't tell me watch Sense and Sensibility, or else I would tell her, go away, no way I'm watching this. So my wife is way smarter. So she tells me, don't watch Dumb and Dumber, but you should watch Happy Gilmore. And this is another stupid movie with Adam Sandler, so I will agree, and I will watch it. And then she tells me, okay, now you watch this movie, so you should go and see Wedding Singer, which is another movie by Adam Sandler. So if I like the first one, although it's kind of romantic comedy, I will still go and watch it. And then if I like The Wedding Singer, then I go to watch Clueless, which is another romantic comedy, so it makes sense. But not many people know Clueless is actually a parody of Emma. So many people who watch Clueless actually then say, oh, I like this story, let's watch the original. And then they go and see Emma. And if I like Emma, anyway, I will like Sense and Sensibility. So that's the way my wife tries to trick me. But whenever I lecture it, a lot of people say, cut the bullshit, your wife just tells you what to watch and that's done, which is also true. But anyway, this is a kind of interesting way where you can link preferences of multiple people, not just one, by actually exploring the item graph and trying to understand which items are similar together and finding paths that connect the items. So this is another approach to recommenders, which we call the graph-based. So let me jump back to my slides. So we talked a little bit about different users and how we can recommend for more than one users. And then the other question we often encounter is, do we know what are the items? And this is a really difficult problem because in Netflix it's easy, you know there are movies, this is the item, and I'm done. And I can watch, if I watch the movie, someone else can watch the same movie and we are fine. But what happens with, for example, we have a customer, Auto1, which is a German used car retailer. What is the chance that the same used car will be bought twice on the same used car retailer? So basically it's almost zero. So if someone buys the car, no one else will be able to buy this car in the next 3 years or whatever until the other guy sells the car. So this is a kind of problem where I'm not sure what's the item, whether the item is a specific car or maybe it's a brand or maybe it's a model and so on. And then you have to be more careful about what's an actual item. Another example from One Kings Lane, it's a Flash retail website where they buy a stock of 100 sofas, they sell all the sofas in some kind of auction, and then those sofas never appear again. So any items that is sold most likely will never be again in the store. And this again complicates what we learned in Netflix because all the item and matrix-based models simply don't work here. So that's need to take into account. Another issue with the type of Netflix data is that Netflix assumes there were numeric scores between 1 to 5 that tells us whether we like the movie. 3 is like so-so and 5 is a lot. But in many cases, we have way richer data. So not just if I like the movie and how much I gave it, but also if it's a product, for example. So I may have watched the product, I may have added it to the cart, I have regretted, and then I removed it out of the cart, I may have sent it to a friend and so on. So there are a lot of events which are happening besides the actual final score for the product. There are a lot of operations that happen. And in many cases, the data we get is actually, or have it as a retailer, is way more complex. So for example, Yelp competition from this year, this data is about restaurant reviews, but the data set is way more interesting because not only we have reviews that this person liked that restaurant that much, we have also textual reviews, we have images of the restaurants, we have links between social networks of users, and we have geographical information and so on. So there is so much richer data, and then the question is how to incorporate everything and make a model that will be more coherent. And almost in any case, companies have all this information, and just giving the rating score is kind of very, very limited. So another demo which I like to show is regarding text data, but I gave it in the morning, so I won't show it again. I show something slightly different now. So let me show you something you didn't see in the morning for those of you who were present. Just a second. So this is a new demo. And what we have here, we are again analyzing user reviews. And typically when you get to some kind of a review website, you typically look into what is the product, what is the average price, and what was the rating. By the way, people on the back, you can try to step in. There is a lot of space here, so anyone who wants to enter is welcome to enter. So what we have here, besides of the average aggregated results, we have much more information that we can actually explore all the different items, but what are the keywords entities that people are talking about. And this is learned automatically from the text. So for example, in this BabySense products, people are discussing the range, the price, the battery life, the signal, and the audio. And what we can do is understand what the people are talking about and what's their average sentiment. Are they happy with the battery life or not? And of course, you can also dive in and see the internals and see what people are actually talking about and whether they love the product or maybe they are concerned about something, and so on. So again, this is a much richer data than just what's the score of the product, because as we've shown here, you can actually score a lot of different aspects of the product, what people are talking about, and what are the actual things they say about it. So now we're getting to way a richer set of information. Yeah, so we talked a little bit about text data, but is it the only thing we can do is just text recommendation? So definitely not. I want to show you one more demo is things you can do with images. And this is a demo we did for a major US retailer. And again, this runs on the cloud on our West Coast instance. So if it's low, blame the network and not the server. So what I have here, we have a store which sells dresses. So I picked a category of dresses. And basically, whenever I see the dresses, I can decide which is the dress that I like more. So let's say I am into floral dresses. I want to buy my wife a floral dress. But this is kind of what I'm looking for, but not exactly what I want. So what I can do is actually click on the image. The image is sent to our predictive server, and based on the image, we can actually get a decision of what are the most similar dresses in terms of the image shape pattern, okay? So as you can see, all of the other dresses have all floral patterns without regard to the color or pattern, but they are all flowers. And the way it works, we have a deep learning based toolkit, and what we can do, we can actually learn what humans see, percept in the class of flower, and then identify similar images that contain the same kind of information. So this is what we call a nearest based model. And this can be very nicely used for fashion. Let me show you one more example. And apologies for the network here is slow. So let's say I like a plain dress, which is a single color. So again, if I like this, we can find all the other relevant dresses, slightly different variation on color, but all they are kind of plain dresses. Okay, so let me jump back to the slides. Yeah. So if we summarize a little bit, what were the insights from Netflix competition? So basically, whenever we increase the accuracy in a fraction on 1%, it really didn't matter and turned into a really complex solution. So in many cases, we don't care about the accuracy where it gets to the very high levels. Also, the solution running time was completely ignored, and that was not the criteria. The criteria was only accuracy, so even if I propose solution that take 5 years to compute, but still it's more accurate, then it was the winning solution. But of course, in practice, we don't want to run to wait for 5 years. Also, in many cases, when we talk about time, we talk about training time, and most of the companies are really unconcerned about training time. It's not interesting. Because if you build a model, for example, for movies, you don't change your movie preferences over a day or a week. It typically takes maybe 3 months or so to change the preferences. And in that case, you can retrain the model. You have enough time, so you don't worry if the model will run in 1 hour or 1 week. It doesn't really matter as long as you can refresh the model fast enough. And also, most importantly, a lot of other considerations are taken into account when implementing recommenders, which are things like ease of use and can I hire C++ programmers to maintain this solution, even it will run 100 times faster and I cannot hire a single C++ person because they are kind of scarce, then I won't go with this solution. So there are a lot of things regarding maintainability of the solution. So I want now to talk a little bit about what I mentioned about ensemble methods. So as I said, the winning solution in Netflix was composed of 107 solutions. And the question is how we combine those methods together. So for that, I have another demo. And by the way we combine those methods is kind of simple. So that's what I like about it. So I like simple solutions as possible. So this is another example with the movies. And what we can show you here, and this is item-based recommender. Looks into the properties of the movies, not the user consumption. Even if I have 0 users in my system, I can still have a good model here because it's looking at the movie properties. So what I can do here is I can pick a movie that I like. Let's say I like Toy Story. And then I get some recommended movies as a default. And as you can see, some of the movies are adult movies, some of the movies are kids movies. So I see that our recommender is not that well behaved. So what I can do here, I can click on any other item. So let's say Run Lola Run. Oh no, something crashed. So yeah, now it's okay. So what we see is what's the comparison between those two items and why they were shown together. So for example, the duration of Run Lola Run is 80 minutes. The duration of Toy Story is 81 minutes. So the computer thinks it's a very good recommendation because I gave you all the movies from the same duration. So you should be happy. And of course, the user doesn't take duration as one of the considerations, unless maybe it's a movie of 5 hours and then I don't want to watch it, but let's say any other duration is really meaningless. So what we can do, we can actually tweak the model and say, okay, duration is not interesting for a human observer, the year of the movie is kind of less relevant for us now, and the title is not interesting. And what I can do, I can rebuild the model, and now as you can see, all the model was recomputed, and now I'm getting way better movies, which are all kids' movies. So now the model looks much better. So let me show you in a little bit how ensemble methods are kind of easy in our framework. And the reason is that we have a data structure which holds all this information, which is called S-frame. It's scalable data frame. So what I have in my data structure, I have a tabular data structure that can contain integer, it can contain vector, dense vectors, it can contain strings and so on. And it contains information about the movies, like the name, the year, the title, how many views, the cast, reviews, images of the movie, and so on. So everything is contained here. And when I build a model that I want to find similar movies, the model building is kind of simple. It's actually one line of Python, which tells me GraphLab nearest neighbors create, and I give the data. And I give some tweaking in order so I can tweak the cost function as I showed you with the duration and so on. So this is very simple because in this original table, I can put results from different algorithms. So the first column here is called latent factor, is actually a result of matrix factorization. So what you can do, you can run algorithm A, get a result as a one column in this table which has dense information. And then I can also have text and reviews and images and so on. And then I can run other algorithms. And when I build the nearest neighbor model, I can actually make an ensemble not only by the user history, not only by the item metadata, but also by the images and reviews and text and cast and whatever things I like to throw in. So in that sense, it takes very easy, just adding things as additional column to my data structures, and then I can build more and more complex models that will be richer and richer in their content. Okay, so let me have a few more slides. Yeah, so of course there are many, many considerations, and I could have given a course of recommender system, so I'm not going to make you too much tired because that's a whole new topic, but there are some interesting aspects that I would like to cover here. So one of the interesting things that we need to be careful is whenever I said we would like the models not to be static, but to update them and have better information. But when, this is a real example, when I looked at cameras on Amazon, so actually immediately I start to get a zillion of cameras and cameras bags and lenses and so on, which is now like too much than what I searched for, so too much of the same. So this is the kind of thing we should be careful in trying, whenever we put feedback, to do it more delicately without annoying the users. Another cool example where we got from an Israeli customer that I won't mention the name, they built a text-based model recommender, and some guy bought car plugs, and eventually he got a recommendation of plug from other type, which is not for the car, but maybe you can use it in the car. But that was kind of funny. So that's the kind of thing you like to be careful about. An interesting lecture by Daphna Shahaf, professor at the Hebrew University. She will be here today. So if you have a chance, I recommend to see her lecture, is how you can recommend similar products. So she built a system that builds on the item data, trying to understand what are similar products that you can switch. And she got very nice highlights of very nice two observations. So first of all, whenever you buy baby products, then there is always a pet product in the store that will be way cheaper and has the same functionality. So that's kind of funny. And the second insight is regarding tub mats. You can always replace them by car mats or mats for staircase. They're going to be way cheaper, and they have the same kind of functionality. So that's kind of interesting insights that are automatically generated by the item properties. Okay, so there are additional issues that should be taken into consideration. I won't get into much detail because I'm running out of time, but of course we could talk in way more detail about some of the issues that happen in the recommenders that you should be careful. One last note that I want to mention here is that we have, as I mentioned in the morning, we have a popular machine learning course in Coursera, and I marked in red the next part that will be out in a couple of weeks is actually 6 weeks about recommenders. So you can do this course for free, a data science course from University of Washington. So anyone is interested to learn more about recommenders and also how to program them using Python. So that's a great course to take to get into a better knowledge about recommenders. So here I will wrap up. And I'll be happy to, afterwards I'll be here until the evening, so if anyone wants to catch me up and have any questions, I would love to engage. Yeah, so the question was, how do you validate the recommendation? There are two types of validations we typically do. The first one is offline. Before we bother the users, we typically split the data and try to validate that the model is not overfitting on a subset of the data. But the best validation is actually online. We typically, when we get a recommender into production, we take a small fraction of the population, let's say 5%, we give them the new recommender, and the rest of the population gets the old recommender, and then we compare the statistical properties of how many products were paid, what was the money collected, and so on, in order to make sure that the new recommenders work better than what we had before.